In today's lecture, we will talk about the transport equation, which we are already familiar with from the last class, and we will convert it to a very useful form which we use for computational fluid dynamics. So when I was introducing the rate of change following a particle, the Lagrangian derivative, we talked about Lagrangian derivative of an arbitrary property phi, and that phi could be given different values, like you can just give it 1 and get an equation. You can give it x momentum, you can take it as y momentum, or you can take it as energy, you can take it as enthalpy. So depending on different you can consider phi to be different properties, and you can use the transport equation to get different equations. So first of all, I'll write down the transport equation. So we will try to write the different forms of transport equation in differential form and integral form. So let's take the property phi. So I think for velocity, which variable did we use? Vx, right? Vx is good. Vx. So in general, there is v. Divergence of rho phi v vector is equal to del dot gamma, which is a constant, which doesn't need to be a constant. That is, we are going to write the diffusion term here. For several practical purposes, we will take this as a constant, but it can also be a function of independent variables. Del dot gamma grad phi. Grad phi is another vector, and s phi is the source term. So if we write down what each of these terms mean, so dou dot t is the usual term which we are already familiar with. It is the rate of increase of phi of the fluid element. And del dot rho phi v, v being the vector, so that is the term represents the net rate of flow of phi out of the fluid element. Now comes the diffusion term. Diffusion term is the rate of increase of phi due to diffusion. The last one is the source term. So that represents the rate of increase of phi due to sources. So that is the whole transport equation. And now this is basically the differential form of transport equation, and we would like to integrate this equation, which is a very important step for the CFD when it comes to finite volume method. Okay, that's a term I think you need to be very familiar with. I may give you a very small introduction to you regarding a method called finite element method. I guess you being having already a bachelor's degree, you already know what is a finite element method and finite volume method. But the finite element, we may not discuss much about finite element method in this course. We will mostly talk about finite volume method. So in finite volume method, it is important to integrate this term over a control volume. So we perform the integration for each term over the control volume. The first term is partial derivative. Second term represents convection, and that is del dot means divergence of rho phi v. When I write it's difficult. When we integrate, we have to write this is basically volume integration, right, in the control volume. So that is integral tau rho phi dot t over cv dv. Similarly, for the convection term, integrate it over the volume, and for diffusion term, del dot gamma grad phi, right, grad phi gamma grad phi is a vector like v vector. Phi is okay, phi, let's say phi is a scalar. If phi is a scalar, grad phi becomes a vector. Phi doesn't need to be a scalar here. In that case, grad phi can be a vector of higher orders also, so that's also possible. Now plus last term will be the source term. Again I forgot to write dv there. Dv plus sy dv, which is the source term. Now we will use the divergence theorem to make a change in this integration. This is actually again a key step, this integration process, and using Gauss divergence theorem to change a few terms is one of the most important and a key step in finite volume method and CFD. So in general, Gauss divergence theorem is Gauss divergence theorem state that if you integrate over a control volume, gradient of a vector, okay, vector, let's call it something, vector v, any vector, and this is integrated over the control volume, and this term will be equal to area integral, means boundary of this control volume. So the boundary surface, if we integrate n dot, n being a unit vector perpendicular to the boundary surface, n dot a n dot v dA. So what does this mean? If we integrate divergence of a vector, any vector v over the control volume, and that will be equal to area integral, which area? Boundary surface of this control volume. So the surface integral of n dot v dA. So if n is a unit vector, normal to surface, n is a unit vector normal to dA at any point. So what will be n dot A? N dot A will be n dot V will be a component of V in normal direction. Normal direction means normal to surface. So if we use divergence theorem here, we can write the transport equation as first term no change. In the second term, this is del dot a vector integrated over the control volume. So we will using divergence theorem here, del dot a vector, it can be written as the surface integral of n dot that vector, now that which is rho phi v dA is equal to again n dot gamma grad phi dA plus integral control volume and also the source term. So this is one of the most important equation for us. How we actually perform this integration is something we will see in the coming classes, and we will discuss the more details about it. Now these two terms, so what is actually the meaning of these two terms here now? So n dot rho phi v dA. So what does that mean? That means the net rate of decrease of phi due to convection across the control volume boundaries. So that's something we can physically see here. I don't know how much time I take to explain. N dot the normal vector dot rho phi multiplied by velocity. So this will become n dot v multiplied by this will make the will give you the rate of decrease of phi due to convection across boundaries. Now we have a new term here. This essentially represents the net rate of increase of phi represents the net rate of increase of phi due to what? Due to diffusion. Diffusion across again the control volume. I mean across the not control volume, the control volume boundary. So let's also write down a simplified form of the equation. So if we have a steady state problem, time dependent terms can be neglected, and we can write a simplified form, which is nothing but only the first the rate dependent, the time dependent term, the first term will be gone. Now so for a steady state problem, integral a n dot rho phi v dA is equal to integral a n dot gamma grad phi n dot gamma grad phi dA plus control volume integral s phi dV. So this is the equation for the steady state problems. For time dependent problems, we also need to integrate with respect to time over a small interval delta t. So so for the time dependent problems, the general equation will be let's say delta t is an interval from t to delta plus t, from t to t to t plus delta t. Now the term is rho phi dV. Derivative of that, and I'm integrating the whole with respect to dt. So you can see that I've switched the operations here. So earlier it was integral of dou rho phi dou t. Now I am performing control volume integration first and finding derivative first. So here there is differentiation first and integration second. Here now I am doing integration first and derivative second, and integrating the whole term with respect to time. So there are two integrations, double integration is there. Now okay, not equal to plus second term now will be integral over delta t and integral over boundary n dot rho phi v dA for surface integration and dt for time integration equal to integral over delta t integral over surface A n dot gamma grad phi integral over surface and time, and the last term which is integral over delta t integral over control volume of the source term s phi dV. So this will be a very general form of the equation which we very commonly use in CFD, infinite volume method. This is basically the integral form of the transport equation. So I'll stop it here and I'll upload lectures topic by topic soon, and not every lecture may be live, so you need to check our website and instructions regularly.